All right. Good morning or good afternoon, everyone. Welcome to the new decade of hot electronic seminar talks. Now, I can imagine that some of you are probably saying, oh, that's not a new decade. The new decade starts in a year. In which case, I'm going to tell you two things. Thing number one is you're technically right. The new decade starts in a year because there was no year zero, as I was shocked to discover about a month ago. And two, nobody likes you. When you correct people like that, no one's like, oh, thank you so much. In any case, welcome to the new decade, and I'm happy to introduce our speaker, the first speaker of the new decade, Simon Henry, a fellow immigrant to Canada, who will speak about the language of a model category.
Okay, well, thank you very much for the opportunity to speak here. So what I want to talk about today is first, I don't think it's something, extremely new. It's mostly, I would say, a new version of old ideas of Makkai that he called fold, like for first order logic with dependent sort, which I try to put in a more modern framework, which is more in line with categorical homotopy theory and the notion of model category. And what I'm trying to do with this small project is basically to try to show that the connection between dependent type theories and homotopy theory, and especially model category theory, might be a bit more general and a bit deeper than what we see with just hot and identity types. So before I go into what is this language of a model category, I will start with one very basic example which has been known for ages. So this is a theorem in category theory that has been proved several times by several different people. So I know a version of Fred and a version of Blanc, but I'm sure there were other versions in history. And it says that if you have a first order formula in a certain language that I will just call the language of category, which in particular should not involve the, equality between objects, then this formula about categories and object of a category is automatically invariant under isomorphism. And by that, I mean that if the formula depends on some parameters, so which lives in some category, and you replace those parameters by isomorphic one in a consistent way, then you that do not affect the validity of the formula on the parameters. And this formula should also be invariant under equivalence, meaning that if you have an equivalence of category and you apply the functor, the underlying functor of the equivalence to the parameter, then that also does not change the validity of phi. So the precise definition of this language will follow from more general thing I will talk about later in the talk. In the meantime, I will just give you a couple of examples of formula in this language. So the first one is, it has one parameter, which is just an object in the category. And it says that for all other objects and for any pair of morphism from this other object Z to our parameter X, then the two morphisms are equal. And so it means that the object is subterminal if the formula is true. And the second example I have is saying that a morphism is a monomorphism. So it has three parameters, two objects and one morphism between them. And it said that every time you have two morphisms from a third object to the domain, then if the composite are equal, then the two morphisms are equal. And you just say that F is a monomorphism. And as you can see, those two formulas satisfy the two invariance property I mentioned before. If you have any object isomorphic to a subterminal object, then it is also subterminal. And if you have any arrow isomorphic to a monomorphism, it's also a monomorphism, and equivalence of category preserve both notions. So those are, simple example of things you can write in this language. And as you can see, at no point in the formula, I'm using equality of objects. Right. So I will just, so the general goal of the talk is that to each Quillen model category, I want to attach a language which has similar property. So the this example, this old theorem of Freid and Blanc that I mentioned should be the special case of the so-called folk model structure on the category of category, which is one of the simplest example of model structure, and whose equivalents are just the equivalence of categories. So I should say that I will work in a classical meta theory, so I'm assuming classical logic, axiom of choice, everything. And the main reason for that is that at the present time, the constructive theory of model category is still fairly new and in its infancy, and it's maybe not yet ready for this kind of work, but hopefully one day we'll be able to make all that completely constructively. And also for the purpose of the talk, I will hide some set theoretic difficulty about size and this sort of thing, just because I want to keep things simple, well, at least the exposition simple. Right, so I need to start with some very basic preliminary. So I don't really know if everybody is familiar with the concept of model category. And unfortunately, I don't really have time to give a complete exposition of what a model category is. So I just want to give you some idea of what it is so that you can at least, if you cannot, if you cannot follow completely what I'm going to say, if you have never met model category before, at least you have an idea of what it is about. Okay, so a model category is a category that has all limit and all co-limit, and which has three classes of map that are called fibration, co-fibration, and weak equivalence. So the very short definition just say that weak equivalence satisfy the 2 out of 3 property. If you have a 2 arrow and they're composite and 2 of them is an equivalent, and the third one is a weak equivalent as well. And it says that we have two weak factorization systems, which are respectively made of the co-fibration on the left and what we call the trivial fibration on the right. That is the map that are both fibration and equivalence. And on the other hand, the trivial cofibration and fibration, where trivial cofibration mean cofibration that are equivalents. And weak factorization means that you can factor any map as first a map in the left class and then a map in the right class, and that the left class has the so-called lifting property, weak lifting property, again in the right class, meaning every time you have a square where the left map is in the left class and the right map is in the right class, you have a diagonal feeder. So it's a fairly technical definition if you have not met it before, but this is basically a framework, one possible framework for a category called homotopy theory. Model category is a kind of one way to present homotopy theory. So for example, you can make sense of what's a homotopy between two maps, especially if they are from a cofibrant object to a fibrant object. So this just means cofibrant means that the map from the initial object is a cofibration, and fibrant means that the map to the terminal is a fibration. You can define the homotopy category of a model category. And if you have heard about infinity category, then this can be seen as a way to present a complete and co-complete infinity one category. So also everything I will say in this talk actually work for weaker notions than Quillen model categories. So if you've heard about left and right semi-model category or weak model categories, and everything apply to them, but you already have plenty of examples if you just use Quillen model category. So there is another small preliminary that I need to talk about, and it's the notion of Cartmel algebraic theory. So I assume most people coming from a type theory background know about them. So it's a type of algebraic theory, but which allow dependent sort, or we call them type, and they allow dependent type. So meaning it's a multi-sorted algebraic theory where some sort can depend on parameters that live in other sort. So again, the completely formal definition of the notion would take a bit too much time. So instead, I will give an example. So the theory of categories, I can see it as a such Cartmel algebraic theory, where I have two sorts, one sort of object or one type of object. And for each pair of objects, I have a type of morphism from X to Y for each pair of objects X and Y. So, I could instead see the theory of category as having just two sorts, one sort of object, one sort of morphism, and then I would need a partially defined composition operation. But with this point of view, I can see composition as a totally defined composition operation, which just take two morphisms in the correct arm and give their composition that is also in the correct arm. So just the typing of the composition already give you the source and target relation on the composition operation. And of course, you have to specify a lot of axiom like associativity, existence of unit, and so on. But this is one way to encode the notion of category without using partially defined operations. So Cartmel theory don't have partially defined operation, but they have dependent type. And you can see, I mean, it's a little bit of work, but you can see that they have the same expressive power as the essentially algebraic theory or partial on theory that will allow for partially defined operation, but no dependent type, in the sense that the category you can obtain as category of model of such theory are the same. But the presentation using dependent type will actually equip the category of model with some additional structure that will be very important for the rest of this talk, and that I will talk about a little bit later. So that, I mean, the Cartmel theory will be our basic tool to talk about this language. And so, okay, when you have a Cartmel theory, you can construct what we call the contextual category or the contextual category of the Cartmel theory. So it's a kind of syntactic category. So objects are context in the theory, like, you know, expression with just a couple of variables that belong to some type depending on previously added variable. And so it's what we call a contextual category. So it's a notion that has been also introduced by Cartmel to study this theory. And it's just a category where certain map called display map, which encode dependent type, admit strictly functorial pullback that encode reindexation of dependent type. And you can see model of the theory as certain functor from the contextual category to the category of set, and more precisely, there are the functors that preserve the pullback along those specific display map. And one last thing I need to say is that I will also consider infinitary version of Cartmel theories, where you can have operation of infinitarities, and you can have type which depend on infinitely many variables, and everything works pretty much the same. So now by the contextual category, I do need to allow infinite context as well. The only difference is that now model are the functors that preserve both pullback along display map and transfinite composition of display map. So, okay, I apologize for those very quick preliminaries that were, you know, too short for people that never saw this notion before and too long for people that are already familiar. And I'll go on to the main topic of the talk. And the main idea, well, one way to present it at least, is that I will add just a layer of first order logic on top of a Cartmel theory. So it's a, you know, fairly, I'm sure also people have done that before. So I'm fixing T such, you know, generalized algebraic theory. So for example, the theory of categories I've talked before. And given a context in the theory, I will inductively define a set, or rather a proper class of formula in that context. So the definition is inductive. And so the base case is that I have that true and false, which I denote by this bottom top element, are formula in any context. If you have a formula in context gamma, then the negation is also a formula in context gamma. If you have some families of formula in context gamma, then their infinite conjunction and disjunction are also formula in context gamma. So I'm allowing for infinite disjunction and conjunction. And finally, I want some quantifiers. So basically, if you have a context gamma prime, which is a gamma plus some variable, and phi is a formula in this extended context gamma prime, then you get formulas in smaller context gamma, where you quantify over the additional variable, either with existential quantification and universal quantification. So if you're working in the context of, you know, infinitary Cartmel theory, you can allow for infinite quantifying over an infinite number of variables at the same time. but only existential quantification on infinitely many variable or universal quantification on infinitely many variable, and no infinite sequence of alternating quantifier.
Can I just ask a quick question?
Yeah, sure.
So in the conjunctions and disjunctions, the indexing set I is just a set in the meta theory?
Yes, yes.
Right? Yeah, okay.
So if you want, it's possible to restrict everything to finitary logic, but the point is, for the kind of theorem I'm going to prove later, the stronger the logic is, the stronger the theorem is. And so I get a more general theorem by allowing for infinitary logic. And of course, all those formula are considered up to some logical rule. I will not list them. One way to write a large number of those rules is just to say that the set, or rather the class of formula in context gamma should be a small complete Boolean algebra. So negation should behave like a negation in a Boolean algebra, and we should have all the condition about conjunction and disjunction that will make this thing a small complete Boolean algebra. And then there is a few additional rows on top of that for the quantifier that I will explain later. Okay, so one very important point about this logic is that I'm not including equality as part of the logic. By that I mean that if I have two terms of certain type, then I'm not saying that x equal y is a formula in any context. So you might be surprised, because generally equality are your atomic formula, and any other formula is somehow built up out of equality and quantifiers. So here the bootstrapping is done using false and true and quantifier. For example, if you have a type in some context, then you can construct the formula there is an element of type A, which is a shortcut for there exists x and in A such that true. And so this is a non-trivial formula in context that can be used as an atomic formula. And you can do the same with universal quantification of false that also give you an atomic formula, which is just the negation of this one. So this is actually the only way to get a non-trivial formula before using logical construction to build more complicated formulas. So despite the fact that we do not have equality in the language, there is a way to still talk about equality for term of a certain type. And this is done by changing the Cartmel theory T that we have fixed in the beginning. And so if we have a certain type in this theory, which has an introduction rule of this form, so some context gamma A is a type, then you can add a new type, so which take two variables of type A, and so I'm calling this type x equal y, so I will call this type the equality predicate for A. And so it comes with some simple axiom. So there should be a reflexivity term. So if you have x of type A, then you get an Rx of type x equal x. If you have a term of type x equal y, then you actually have that x equal y. And if you have a term of type x equal y, then so by the previous rule x equal y, but you also want that T is the reflexivity term Rx. So this is just a definitional equality made into the language. So when you change the theory this way to add this equality predicate for A, that is not going to change the category of model of the theory, because the only way this type can be interpreted is as the equality predicate of the type A. So it does not affect the category of model, but it will affect the language in the way I've defined in the previous slide, because now you have this additional type which you can use for quantifying. And so, for example, you get a new formula, which is there exists a term of type x equal y, which you can use as a definition of the formula x equal y. And so as soon as you have such equality predicate on the type A, you have the formula x equal y for a variable of type x and y.
I have a question.
Yes.
Is the equality on the right the same as the equality that you defined, or is that some other kind of equality?
So
I mean, the
yeah.
equality like t equals rx is the same equality, or what is it?
So the equality that is on the right side of the deduction symbol is the equality in the sense of, in a cartwheel theory, you can have axiom saying that two terms are equal. And so I can add axiom that say that two terms are going to be equal. So it's like definitional equality.
But you said you don't have usual equality formula.
I'm not sure I understand the question. So like
at the top of the slide, you said that x equals y is not a formula, right?
Yeah. Yeah. So when I say formula, I mean in the sense of the previous slide of this notion of formula I have defined. But I'm not saying that the axiom of the Cartmel theory has to be formula in that sense. The axiom of the Cartmel theory were defined, in Cartmel's paper and does not involve this definition. And you can use formula that have equality as axiom of the theory. Is that clear?
Yes, I think. Thank you.
Okay. So I'll take, I'll come back to this example of the theory of category. So now what I'm taking precisely the Cartmel theory of category, which has two basic types, object and morphism from one object to another object, as mentioned before. And I'm adding on top of that an equality predicate for the type. So equality of two morphisms between two given objects become part of the language. And the formula, in the sense I've defined for this specific theory, are exactly the formula to which this theorem of Fried and Blanc that I've mentioned on the first slide apply. So those are the formula in this language are automatically invariant under isomorphism and under equivalence of categories. And so for people that have heard about Makkai fold, I'm just mentioning that the framework of Makkai fold is a special case of this, where you consider a Cartmel theory that has only type introduction axiom, so it has no term, no type equality axiom, no term equality axiom. Well, it cannot have any non-trivial term equality if it has no term. And on top of that, you choose some specific type and you give them an equality predicate, but you cannot have a type that depends on a type that has an equality predicate. Well, except the equality predicate itself, of course, because it depends on the type. But the type that have an equality predicate have to be at the top of the dependency hierarchy of type. So, okay, if you've never heard about this first order logic with dependent sort, that's not a very important remark, but that's exactly what the framework of Makkai is exactly this. Right. Okay, so I will make a small digression at this point. So I've already showed you that when you have a Cartmel theory, you have this additional structure, this notion of formula, and that you can have two different theories that have the same model. For example, you can add equality predicate without changing the category of model, but which have different notion of formulas. So this is the first example of a structure that you have on a Cartmel theory that is not seen by the category of model. And I want to show you another example of this structure, which is that if you have a Cartmel theory, its category of model come with a certain completely canonical weak factorization system. So the left class, I will call the map cofibration. And they are exactly the retract of morphism that are obtained by freely adding elements. So it's a morphism from A to B, where B is obtained by freely adding elements of various type to A. So various type mean in the sense of the theory. So let's just take an example. If I still have this theory of category where I have object, morphism, and the equality predicate for morphism, Then freely adding element mean I can freely add object, which has the effect of putting, an isolated object to the category. Or I can freely add morphism. So for example, I can freely add morphisms that will connect the new object I've added to old one, or maybe it would be morphism between the old object. And I can also freely add element in the equality predicate, which would have the effect of taking two morphisms that are already parallel with the same source and target and making them equal because I'm adding an element freely to the equality predicate. So when you combine this free construction, you can do pretty much anything you want on morphism because you can freely add morphism and make any two morphism equal. And you can freely add objects, but you cannot make two objects equal. So the class of functors between categories that you will obtain this way are exactly the injective on object functors. And so the right class of this factorization system, which I will call the trivial fibration, they are the map which has the so-called term lifting property. Which I think it's a notion that has been considered for several different reasons in the literature. So it's a bit technical. It says that if you have a morphism F between two models and you have some type axiom in your theory, so which says that A is a type in context gamma, and you have some variable in X of gamma, so which is the evaluation of X on context gamma. So it's a set of all choice of interpretation of the variable in gamma as element of X, and you have an element Y in Y or in context gamma A, so it can be seen as an element of Y gamma together with a T, which is a choice, a reasonable choice for a variable of type A in Y. Then you can lift this as an element of X gamma A, which has the correct, where the first component is X and K is sent on T by the map from X to Y. So, okay, it's a bit technical, so I'll come back to my example. So a trivial fibration between category, it would have to have the lifting of object. So it has to be surjective on object. It means every time you have an object in the target, you can find an object in the domain that is going to be sent on it. Then it has to have the lifting of morphism. So it means that every time you have a morphism in the target that is between two objects that are image, like that are of the form f of x, f of y, then you can find a morphism between x and y that is sent to this morphism. So it says the functor is full, surjective on the onset. And the last condition is that it has to have the lifting for the equality predicate. And this exactly means that if two morphisms became equal, two parallel morphisms with the same source and target became equal in the target, then they were already equal in X, and so it means the functor is faithful. So in the end, for this theory of category with equality predicate on the onset, the trivial fibration are exactly the fully faithful surjective on object morphism. So we have this weak factorization system on any category of model of a Cartmel theory. And as you can see, it depends on the theory and not just on the category of model, because
Can we have a question
yes?
somewhere? Sorry.
Yes, I have one question. So if we start from a limit theory, there is no way to see this factorization system on the category of models. This is something.
Okay, so if you start from a limit theory, the problem is that there are different ways to choose a Cartmel theory that will have this theory, which will have the same category of model. And so you will get different, you can get different factorization system on your limit theory. So for example, if I come back to this example of the theory of category, if I did not have equality predicate on morphism, then the cofibration would only be able to freely add morphism, and I would not be able to collapse them, and so there will be a lot fewer cofibration.
Thank you.
Okay. Yes. So, okay, so if you know what it means, this factorization system is cofibrantly generated, and it has exactly one generator per type axiom in the theory. So we have a fairly explicit set of generator, and you can actually use that to go the other way, try to guess what Cartmel theory could have generated a certain factorization system you're interested in by looking at the generator of the factorization system and saying that those should be the type axiom of your theory. So it's relatively easy to go backward as well. Start from the factorization system on, let's say, for example, the category of model of a limit theory, and try to guess what Cartmel theory would give this factorization system. You cannot do it with any factorization system, but in practice, you can very often do it. Okay, this is this example of the theory of category I mentioned before. And as I said, cofibration are the injective and object functors. Trivial fibration are the fully faithful and surjective and object functors. And if you know a bit about model category, you know that those are exactly the cofibration and trivial fibration of the Folk model structure on CAT. And that's where the connection between model category and Cartmel theory is, in my opinion, which is that this natural factorization system that you get on the category of model of a Cartmel theory is the one that we use in model category theory to get the cofibration and the trivial fibration. And as we say, this precise theory of category is the one for which the theorem of Freid and Blanc applied. And so this is the general pattern that I want to talk about in this talk. So I'm quickly mentioning this other example of fold. So if you have a fold signature, so it's, it corresponds to the specific Cartmel theory I've mentioned in the previous slide. Then, so the category of model is a presheaf over the directed category of basic type. And so the cofibration, they are exactly the map that are injective on all types that do not have an equality predicate and can be whatever you want on the map, on the type that have an equality predicate. The trivial fibration, they were considered by Makkai, did not give them a name because they mixed two different notions that he was considering. But they are the maps that he used to define equivalence model. So Makkai defined two models of a fold signature to be equivalent if there is a span of trivial fibration in the sense I just defined, connecting them. Right. So, so I can give a more conceptual, or maybe I should say more categorical definition of those formula I have defined. So remember, I had a fixed Cartmel theory, and I had a notion of formula in context for this theory. So if I call C the category of context, and I can use either the finitary or the infinitary version. So I'm going to define in the notion of complete Boolean algebra over C, where C is the category of context. So it is a functor from C up to bool, the category of possibly large, small complete Boolean algebra. By small complete, I mean a Boolean algebra that has small supremum and infimum. So I want, in addition, that for every display map, so the map that encode context dependency, type dependency, then the functoriality along this map, so which I denote by P upper star, and that go from By to Bx, so it's a contravariant functor. It has to have a left adjoint, which I call exist P, because it's supposed to correspond to existential quantification for formula. So okay, I want this left adjoint, and I want to have a so-called Beck-Chevalet condition, saying that if I have a pullback of a display map, so in this diagram, P is a display map and G is any map and the square is a pullback, then I want to have the formula written down below, which is that if you start from a formula in context X, if you start with, so the main example of this complete Boolean algebra over C would be formulas later, so that's why I'm saying formula, but it's just an element of the Boolean algebra evaluated at X. So if you first do existential quantification along P and then pull back along G, or if you first pull back along F and then do existential quantification along P prime, then you should get the same element of B of Y prime. So we call this a Beck-Chevalet condition. Okay, so this is just a definition. I have this notion of Boolean algebra over C. There are special presheaf of complete Boolean algebra that have those left adjoint and satisfy those Beck-Chevalet condition with respect to pullback of display map. So it should be, if you have, if you know about hyperdoctrine, it's very similar. It's just in a hyperdoctrine you consider Beck-Chevalier condition for all pullback square and not just pullback along display map. So it's if every map was a display map, that would be pretty much the same as an hyperdoctrine, or at least some kind of a hyperdoctrine. And so the main theorem is that given a Cartmel theory, see its category of context, then this is a functor which associate to each context of the theory is a set of formula, first order formula in context gamma, where the functoriality is given by reindexing. Then this is the initial complete Boolean algebra over C. So this gives a way to give a purely categorical and non-syntactical definition of this object of formula in context gamma. It is the initial complete Boolean algebra over C. Maybe just a quick remark. You can, if I come back to the definition of complete Boolean algebra, you might be surprised by the fact I'm only talking about existential quantification, while earlier in the definition of formula I had both existential and universal. But this is just because I'm working with Boolean algebra, and so universal quantification can be defined in terms of the existential quantification as, you know, the negation of for all the negation. And so I don't need to put both left and right adjoint. I just need left adjoint, but the right adjoint will be there because of the Boolean structure. So I could give a definition with right adjoints instead, and that would be completely equivalent. There was something else I wanted to say. I can't remember, so I'll just go to my example. So what's interesting to define the set of formula as an initial object is it implies that every time you have a complete Boolean algebra over C, then you get a natural morphism from the set of formula to this object, so an interpretation of the formula. And so the most obvious example of that is that if I take X to be any model of the theory, so it's a functor from the category of context to sets that preserve pullback along display map and transfinite composition of display map if I'm in the infinitary case, then I can construct a specific complete Boolean algebra over C, which I call P of X, so P of X evaluated on a context gamma is just the power set of X gamma. So the set of all subsets of X gamma, and functoriality is given by pullback. I mean, I'm using the contravariant power set. And so as X is a covariant functor, Px become a contravariant functor, and you can check that the left adjoint I've mentioned before exists, and that you have the Beck-Chevalier condition. And so in particular, you get a unique morphism from the Boolean algebra formula to Px for any X. And this is the morphism that sends any formula in context gamma to the interpretation of the formula that is the set of elements of X gamma which validate phi. So I remember, if you're not familiar with Cartmel framework, X gamma is the set of ways to interpret the variable encoded by gamma in X. And so if you have a formula in context gamma and an element of X gamma, it makes sense to ask whether the formula is true or false for this specific element. And that's what this canonical unique morphism from F to Px give you. Okay, now a remark is that if I have a morphism between two models, then I get a pullback map which go from Py to Px, which take any subset of Y gamma and put it back as a subset of X gamma along F. And it's automatically functorial with respect to the contravariant functoriality, the one given by pullback of sets. But in general, it has no reason to be compatible with the covariant functoriality given by existential quantification along display map. And if you look a bit at what it means, that a map would be compatible to those existential quantification, you observe that a morphism of T model, so for a given morphism of T model, this induced morphism between Py and Px would be a morphism of complete Boolean algebra over T, that is, would be compatible to this covariant functoriality given by existential and universal quantification, if and only if the map F is a trivial fibration, that is, it has the term lifting property. So trivial fibration in the sense of the factorization system on the category of model I've constructed before. So what I mean is that those two additional structures that we had on Cartmel theory on top, that we don't have for limit theory, for example, given by formula and trivial fibration. They are connected by this lemma. The trivial fibration somehow preserves interpretation of formula. So when I write it like this, it sounds maybe not clear what it means exactly, so I will rewrite it in a different way. And so I attribute the theorem to Makkai because that was one of the main results of Makkai work on folds in the case of fold signature, and the proof is essentially the same. It's just in this slightly more general framework. So if F is a trivial fibration between two models, and if phi is a formula in some context gamma, and you have X an element of X gamma, then it satisfies phi if and only if F of X satisfies phi as an element of Y gamma. So trivial fibration preserve and detect a validation of formula completely. So, and the reason for that is just that because of the previous result, if you have a trivial fibration between two models, then the morphism from Py to Px given by pullback is a morphism of complete Boolean algebra. And so the triangle of the canonical map which give interpretation of formula automatically commutes because those maps are unique. And so if you have a morphism here, the composite of the first unique map with the morphism is again a morphism, so it is equal to the other unique map. And when you look at what it means, it just says that pulling back along a trivial fibration preserve interpretation of formula, and the explicitly, if you write that explicitly in terms of elements, it gives exactly the theorem above. So it's just a formal thing from this the lemma of the previous slide. So that, to the way I understand Makkai work, this was the main result in Makkai, and that's why I use this notion of trivial fibration to define equivalence of model as span of trivial fibration, and does lots of other things based on this idea. But from this point, I will take a slightly different route. And instead, I would assume that my category of model, the category of T model, has a bit of additional structure, and more precisely that it has equivalent model structure, where the cofibration and trivial fibration are as defined before. So they are the one given by the Cartmel theory. So then now I can see, element of X gamma when X is a model and gamma is a context. I can see them as morphism from what I call F gamma to X, and F gamma is just the free model generated by the context gamma. So it's a cofibrant object, kind of by definition, because gamma is specifying some variable, and you just add freely one element for each variable in context gamma, and cofibration will define as the morphism that can be obtained by freely adding objects. So if you start from nothing and just add three elements, you get a cofibrant object. In fact, if you're working in the completely infinitary case, those are essentially all the cofibrant objects. More precisely, the cofibrant object should be retract of those three objects on context. And so, yeah, element of X gamma, you can see them as morphism from F gamma to X. And in particular, you can ask whether two elements of X gamma are homotopic or not, because they are morphism in the model category. And so there is a sense in which they can be homotopic. And this is especially reasonable to do if X is fibrant, because homotopy is specifically well-defined for map between a cofibrant object to a fibrant object. So if X is fibrant, those are mapped from a cofibrant to a fibrant object. So we have a notion of homotopy for elements of X gamma. And so the main theorem of this talk, I would say, is that under this assumption, so if X is fibrant and two elements of X gamma are homotopic, then they validate the same formulas. So if I have a formula in context gamma and X and Y are homotopic, then phi of X is equivalent to phi of Y. And so if I go back to this example of the theory of categories and the Folk model structure on categories, then you recover that formula in the theory of category are invariant under isomorphism, because homotopy in the Folk model structure correspond to isomorphism. And same thing, you get invariance for weak equivalence. So if you have a weak equivalence between fibrant model, Then for any element of x gamma, you have that phi of x hold if and only phi of x hold in y. And so this corresponds to the invariance under equivalence of category, but now for a not yet a general model category, because I'm still assuming that they have a model category on a Cartmel theory, but still something fairly more general than the case of categories. And that also, yeah. So I'm just saying a very quick word about the proof of the theorem. It's actually completely formal and very simple from the previous observation. So for example, for the second point, we use that in a model category, every weak equivalence can be factored as a retract, weak equivalence between fibrant objects can be factored as a retract of a trivial fibration followed by a trivial fibration. And so because trivial fibration preserve validity of formula, we can deduce that weak equivalence preserve validity of formula. And for the first point, it's very similar. It's because homotopy can be encoded using path object, and the leg of a path object are trivial fibration. And so by using the validity in the path object as an intermediate, you can jump from phi of x to phi of y by combining two trivial fibration. So those are very, very simple formal consequences of this theorem that I've attributed to Makkai before. Okay, so most models that we use in practice, like, I don't know, the model structure on simplicial sets, both the Quick-and-Quillen and the Joya, or chain complexes, are model categories of this form. They are model category on the category of model of a Cartmel theory with the correct factorization system. But I promised you that I would make sense of this for a general model category, so I need to extend a little bit this. So one way to do it is to say that you can always build, so if you have a model category M, you can always build some possibly infinitary Cartmel theory such that the category of context would be equivalent to the opposite of the category of cofibrant object, and the display map would correspond to cofibration. And then you can see that if you use the first order language as I've defined for this Cartmel theory, then you get similar result in M. So that's one way to do it. But in practice, it's sometimes, you know, not very convenient to try to construct such a Cartmel theory, or very, you know, it's a very abstract construction. One other way to do it is that if you take the purely categorical definition of formula, you know, as the initial complete Boolean algebra over the category of context, well, you can see that in the previous points, the object of formula do not depend on the choice of the Cartmel theory. It only depends on this category of cofibrant object and cofibration between them. And so the purely categorical definition, you can make sense of it directly on M without ever mentioning a contextual category. And you will need to invoke a contextual category only if you want an explicit syntactical definition of what your formulas are, which sometimes is useful, but in practice, you know, you can still kind of write formula without choosing the Cartmel theory and just using the cofibrant object of the model category. And so with this definition, everything I've mentioned so far worked exactly the same when proved directly in terms of M without ever mentioning Cartmel theory in the first place. It's just less syntactical and purely categorical. So in this point of view, contexts are just cofibrant object of M. Formula are given by a functor that goes from the category of cofibrant object to the category of small complete Boolean algebra. And you want to have left adjoint along cofibration. So left adjoint of the functor for the functoriality along cofibration. Models should be general object of M, though as we've seen before, most of the interesting theorem only apply to the fibrant model, not all model. And saying that you have an element of X gamma just means that you have a map from the cofibrant object gamma to X. And that's the general framework for a general model category. So you get this formula are defined as element of this initial complete Boolean algebra over the category of cofibrant object, and you get all those theorems of where you have a notion of interpretation of formula and validity of formula, and those are preserved by homotopy and weak equivalences between fibrant objects. But as I said, for most concrete example, you really have an explicit Cartmel theory given to you. And you can use the syntactical version of formula in the Cartmel theory. So there is one last question that I want to discuss, and I think I still have a few minutes. So now that we have this language for any model category, how does that behave if I go from one model category to another? How is it functorial in model category? So the most natural notion of morphism between model category are the so-called Quillen adjunction. So they are pair of adjoint functor, where the left adjoint functor preserve cofibration and trivial cofibration, and the right adjoint functor preserve fibration and trivial fibration. And so if you only have the Quillen adjunction, so with L the left adjoint, R the right adjoint, and M and N two Quillen model category, you can make the left adjoint functor act on formula. So you can define something which takes a formula phi in M in context gamma and give you a formula in N in context L of gamma. And I'm going to call this construction L. It can be either defined using the universal property of the object of formula, or by induction using the syntactical definition of formula if you have it. It's, I shouldn't say characterized because it does not completely characterize it, but it satisfies the following fact, which is that, so if I want to know whether the formula L of phi is validated by some element X, so X should be a morphism from L gamma to X, then this is L phi of X will be true if and only if phi of X tilde is true, where X tilde is the corresponding element under the adjunction, so the corresponding map from gamma to R of X. So we have some kind of adjunction property for this action of formula in this sense. Right, so this gives at least functoriality. If you have a Quillen, left Quillen functor between model category, you can use it to transport formula from one model category to the other, and it says something about action of the right adjoint on model. Now the interesting question is what happens if I have a Quillen equivalence, so a Quillen adjunction which induces an equivalence between the homotopy category of my two model categories. And that you cannot say anything in general. You need to first identify formulas that have the same semantics in fibrant object. So I'm defining an equivalence relation on formula. I'm saying that phi is equivalent to psi if phi and psi have the same interpretation in all fibrant objects. So for every fibrant object and for every element of the fibrant object, the validity of phi on this element is equivalent to the validity of psi on this element. So it's a, a semantical equivalence relation. And so I'm defining fh of gamma as the quotient of f gamma by this equivalence relation. So you can check that it is still a complete Boolean algebra over C as before, but we have to identify formula that where the semantics don't see the difference between the formula. And then you have that if you have a map between two cofibrant objects or two contexts that is a weak equivalence in the sense of the model category, then the set of formula in gamma and in gamma prime identified by this equivalence relation are the same. So equivalent context give you the same formula, at least up to semantical equivalence. And if you have a Quillen equivalence between two model category, then the construction I've mentioned on the previous slide that said formula in context gamma to formula in context L of gamma also induce an equivalence between formula in M in context gamma and formula in N in context L gamma. So up to semantical equivalence, Quillen equivalent model category have essentially the same formula, so you can express the same thing with this first order logic. Okay, now there's something I should say, which is that up to this point, everything was extremely formal, extremely easy, either direct induction of formula or using the universal property of the objective formula, or actually most of the time you can use both, and both are very simple to use to prove everything. This last point about quid and equivalence is, at least to me, surprisingly hard, and the proof is very non-explicit. I couldn't give a proof of that by a simple induction of formula. To be even more precise, the injectivity of the map was easy to prove, but the surjectivity was very hard, and I couldn't make an easy induction of formula work. I had to use very complicated technique of model category theory that actually some of them are not written yet, and that's why all that is not written yet, because it relies on other things that are not ready. And what it means to me is that even if quid and equivalent model category, we have those language are equivalent, it's in practice, it can be very hard to transport formula along a right adjoint equivalence. So the transport along left adjoint was very formal and defined on the previous slide, but going backward along a right adjoint is not explicit, very hard, and you only get a formula up to the semantical equivalence relation, so there might be some choices to make in the construction of the formula. So it's possible, but it's probably hard. Though it can just be that I've missed a simple proof and that it's actually easy and I missed it. That's definitely a possibility. So I think I'm almost out of time, so I will just mention one example other than the language of category, and this is the Joyal model structure on simplicial sets. So it's a model structure on the category of simplicial set with fibrant object are the quasi-categories, or the infinity one categories. And the homotopy theory corresponds to the homotopy theory of infinity one category. So the equivalence between fibrant objects are really the equivalence of infinity one category and so on. And so if you just directly apply everything I've said to this model category, then you get a language of quasi-category. So we are in the special case where this is a category of model of a Cartman theory with a correct factorization system. So we have the nice syntactical presentation of everything, and it gives you a language to talk about quasi-category, where you can talk about the simplices, the n simplices for all n of the quasi-category, which have to satisfy some satisfy some specified boundary condition, like you can, for example, consider the type of all one simplices with specified source and target, or the type of all three simplices where the boundary two simplices were previously specified. But you cannot talk about equality of simplices in general, other than the equality needed to specify the boundary conditions. What you can do, however, is to talk about homotopy between simplices using higher dimensional simplices. And so by the general theorem I've mentioned, this language of quasi-category is automatically invariant by isomorphism and equivalence of quasi-category. And you can observe that a lot of notion developed for quasi-category, like, I don't know, limits, co-limits, final objects, and so on, are very naturally written in this language. In fact, if you, for example, open Jacob Lurie's book, Higher Topos Theory or Higher Algebra, you will see that most definitions are in this language. And so you get a general formal statement that all those things are invariant under equivalence of category and under homotopy, which most of the time is either a lemma proved in Jacob Lurie's book, or something that is admitted because we have already proved thousands of similar lemma before, and we skip a few one after some time. So I think I'm out of time, so I will stop here, and thank you very much for your attention.
All right, well, thank you very much. I mean, if you have one slide, I'm assuming the last slide says thank you.
No,
one more.
No, it was a couple of additional examples, the projective model structure on chain complexes, and something about two different model structure that give two different language for the same equivalence, but that's not very essential.
Okay, well, I suggest this. We thank Simon for the talk. We're doing silent applause, so we're not unmuting everyone, but I'm just gonna clap to the camera. And yeah, okay, we're gonna move on to the question and answer part. And I'd imagine some people may have questions about the last two slides, because I think a question that I had in mind is exactly about slide 22. But I'll let others ask questions first. So if you have a question, just unmute your microphone and ask the question, please.
Hi.
Hi.
Thanks for the talk. So what are some of these results on model categories, which you mentioned haven't been written down yet?
Right. So it's mostly something, so I've given a talk last summer about the model category of combinatorial model category. So I need to use a cofibrant replacement. I need to use those cofibrant combinatorial model category and cofibrant replacement in that sense. So that's, with this, I can prove the theorem for combinatorial model category. And then I need to use another result, which is some kind of combinatorial approximation theorem, which say that if you have a general model category and you have a certain type of diagram in it, then you can find a combinatorial model category such that the diagram you have already live in this combinatorial model category. I mean, I could also write a very technical proof that implicitly use those things, but I wanted to wait until the other two were written.
I have a question, if we're done with that one. So the slide you're displaying now about the Joyal model structure, are there other presentations of infinity one categories that give a different interesting language for studying infinity one categories?
Yeah, absolutely. I mean, any model category you have that present infinity one category would give you a language. So for example, if you use, I don't know, complete single space as bisimplicial set, then you will get this language where you have two different types of simplices, one corresponding to the topological direction and one to the categorical direction. So you will actually get a richer language where you can already, in the language, you already have the notion of invertible cell present using the topological direction. So you will get, a richer language where the notion of invertible cell is already present without having to be defined from the non-invertible ones.
But then I guess since those are equivalent, when you put this equivalence relation on the formulas, you end up getting isomorphic sets of formulas.
So for example, in this example I just said with a complete single space, it will be because you can define what's an invertible cell in the language of quasi-category. And so everything that uses this additional notion of invertible set can be encoded without it by using the explicit definition of an invertible cell as a cell having an inverse. Right.
Okay, so sorry to keep going, but then this also makes me think that this equivalence relation you put on the formulas, testing among fibrant objects, the semantic equivalence, this must collapse a lot of things together, right? I mean,
yes and no. So if I was working with finite array logic, I could probably get rid of this equivalence relation by adding some axiom, like saying, for example, the axiom that imposes that the object you're talking about is fibrant, because there would be some kind of logical completeness theorem that would say that semantical equivalence relation can actually, two things are semantically equivalent if and only if they are provably equivalent. The reason why I'm not doing that is that completeness theorem for infinitary logic are a lot harder, and I didn't want to get into this kind of difficulty, and so I decided to collapse everything up to semantical equivalence relation. So before this semantical collapse, you already have the two formula identified if they are provably equivalent. And this already covers a lot of...
Right. Okay, thank you.
Right. Anyone else?
I have a question about the main theorem of this talk, as I called it.
Mm-hmm.
Can you open this slide?
This one?
Yeah. Yes. So the notion of homotopy between maps into fibrant objects depends only on confiberations and not on the whole model structure, right? So I mean,
well, it depends on the cofibration and trivial cofibration because you need to specify cylinders.
No, confiberations and trivial fibrations. I mean, cylinders are defined only.
Yeah, right. Yeah, you're right.
So basically, what I'm trying to say is that you can define this notion for. You don't have to assume the existence of model structure. So you can talk about.
But note that in the assumption of the theorem, there is that X is fibrant.
Yes. So basically, the question is whether this is true. I mean, you can have many different model structures, but the notion of this homotopy will be the same for. I mean, for if you have like minimal model structure where you have as many fibrant objects, that it will be true for all of them, right? So the question whether do we need the model structure at all? Maybe it's true for any object or not. You do need the existence of model structure.
So absolutely. So if we assume the existence of minimal model structure, which I think is true under the Makkai principle, and it's not known if it's true under ZFC, then the theorem would be true without assuming the existence of a model structure for objects that are fibrant in the minimal model structure. Though it might be hard to guess what are the fibrant objects of the minimal model structure without computing it. So I don't know if this is useful or not.
But I mean, whether do we need to know that it exists? Maybe this theorem is true for all objects or not.
You really need to know that the objects are fibrant in some model structure for the proof. So that's not going to work without talking about the minimal model structure or some model structure.
Right. Thank you.
Could we see the last two slides?
And Sima, your view of the participants is overlapping the slides.
Oh, sorry. Was it like that during all the talk?
No.
Just
now it's fine.
Last.
Okay. Okay, so the other example is fairly simple, is that if you look at the projective model structure on chain complex, then you'll get a language. So in the projective model structure, every object is fibrant, so you can talk about every object. And you can talk about chains living in some degree. You have also group operation on chain. You can talk about cycles more generally. If you have a chain T, you can talk about the type of X whose boundary or co-boundary. I should say boundary here because I said chain complex is T. But in general, you cannot talk about equality of chain. You can only talk about whether two chains are the difference of two chains is a boundary or not, for example. So this is very similar to the previous example of the Joyal model structure. And we also in the case where this is a model category structure on a category of model of a Cartman theory. So the last example is maybe a bit more interesting. So it's a bit artificial, but so I'm considering the category of pairs of category and those with a functor between them. And so this has two model structures. So you can see them as two different 3D model structure depending on if you see isomorphism as going up or down. In both cases, for the two model structures, the equivalences are just the pair, the squares, where both map are equivalents. For one of them, every object is fibrant. And for the other, the fibrant object are the one where the functor f is an isofibration. That is a fibration of the fork model structure. And so you get two different languages for talking about functors. So the first one, you can only use the language of C1 and C2, the two categories separately. And the fact that you have, if you have an object of C1, you can send it, and it's also an object of C2. And the second language is a bit richer, and it lets you talk in addition. So if you have an object, so it's wrong in the slide. If I have an object in the target, so if I have an object in C2, I can look at the type of object that are sent. Oh no, that was correct in the slide. If I have a Y in C2, I can look at the type of all X which are sent to Y. And so I can, for example, ask if there is an object that is sent to Y exactly and not up to isomorphism. So for example, this second language lets you formulate the notion of Grothendieck fibration, while in the first language, you can't formulate the notion of Grothendieck fibration, you can only formulate the notion of strict fibration, this Grothendieck fibration up to equivalence. And so the fact that the two model structures are quill and equivalent shows that you can anyway always translate a formula in the second language into a formula of the first language, so you can get rid of those additional semantical things. And so, for example, the typical example of that is that the notion of Grothendieck fibration would be translated to the notion of street fibration. And what it says is that a street fibration that happened to also be an isofibration would be a Grothendieck fibration. And yeah, that's, I think, all I wanted to say about that example.
I know if there was a question from the MSRI about this slide, or did you just want to see it, or?
Yes, thanks.
Okay. So maybe I'll ask a question, since I think the slide didn't say what I thought it would. So I'm wondering, like, which way should the applications of potential applications of this language go? So, like in classical topos theory, maybe you can show that two toposes are equivalent if they classify the same theory. That's one of, like, I think, like the biggest application of classifying toposes. And then something that's very much along the lines of what you're doing here. Peter Lamstein and I have this paper on the homotopy theory of type theories, and we also consider like a left semi-model structure on the category of models, and we kind of work the other way around. So we can say that two dependently typed theories are equivalent if the categories of models are quill and equivalent. So I was wondering, you probably said it in the talk at some point, but I just wanted to check.
So, I mean, it will indeed be true that if two model category, or at least that if you have a quill and functor that induce an equivalence between the language, then it's a quill and equivalence. But that's very much overkill. I mean, it's essentially trivial that it's true, and it's a lot harder to show that the quill and functor will induce an equivalence on the language than to show that it's a quill and equivalence. Like saying that it's a quill and equivalence only involve equivalence of very specific formulas and not all infinitary formulas. So, I mean, the type of application I had in mind for this work was really, you know, just this generalization of this theorem of Blanc and Frey, that if you want to talk about some kind of higher structure, and if you only, you know, talk about it without breaking the equivalence principle, so without talking about equality between things you shouldn't say they are equal, then everything is automatically nicely homotopy invariant, and you don't have to prove it every time by hand. That's really what I had in mind here. I'm not sure there are interesting applications in the direction you have in mind here. Maybe there are, but I can't think of anything.
All right. We still have some time, so if there are any other questions, you should entertain those now. Maybe I'll ask one other quick question. Have you thought about the relation between your work and what Dimitrios Tsementis was doing? I don't know if you.
I don't know. I've watched the talk, so I know why you're asking, but I'm not exactly sure what to say here. I don't know.
Okay. Yeah. Okay. Okay. This is the last call for questions. Then, please don't be shy at this point. Okay. Well, if there are no further questions, then let's thank Simon again. So again, silent applause. Yeah, okay. So I think that's it for today. So thanks a lot for the talk. Thanks a lot for attending, everyone. And yeah, I think we can stop the recording and we'll see everyone in 2 weeks.